אנחנו מאוד מאוד שמחים. English, okay. So we're delighted to have Lubotzky today here today with us. Mathematician since 2021, faculty member at Weizmann Institute. He's also an Israel Prize laureate for his achievements in mathematics and computer science, including in graph theory. His paper recently on explicit lossless vertex expanders won the Fox 2025 Best Paper Award. And he's also a former politician and on Knesset. So thanks so much for joining us.
Thank you. Actually, after I saw that you described my big achievement as this recent paper, I thought that you invited me because of that. But you invited me so long ago. Meanwhile, my student was here and gave a talk on that paper. So, and it's too technical, I think, anyway, for a colloquium. So I have to confess that I'm a little bit excited, but a little bit nervous, because all my life I'm kind of jumping between computer science. Well, I'm a pure mathematician by training and deep in my art. But over the years, I had kind of an ongoing love affair with some computer science, but somehow, and I gave many talks in Fox's talks, computer science seminar, but I realized suddenly, if I'm not mistaken, I never gave a colloquium talk in computer science department. So even though I'm close to 70, you see there is something new for everybody, but I decided to give some kind of an experimental talk. So I hope it will work. It will be more like a story. For me, it's kind of a lifelong story, but I want to give you a kind of survey, a non-technical talk about the interaction between pure mathematics and computer science. Now, of course, mathematics is essential for many areas in computer science, but what I want to point out that sometimes notions, maybe it's less known that notion which started in computer science had also a deep and important influence in pure mathematics. I will try to be very non-technical, and I will wave hands for most of the time. Sometimes I will make some pictures. Anyway, let me start. First of all, as you can see, I'm a mathematician. I'm writing on the blackboard. I hate slides. Sometimes I must. But if possible, I prefer a blackboard and chalk or even low tech. Anyway, probably the most fruitful area of interaction between pure mathematics and computer science is the area of expanders. Expanders graph were defined in the late 60s in Moscow. Usually the official history is that it was started by Pinsker. Some years ago, it was discovered that Kolmogorov and Brezhnev talked about expanders even slightly earlier. Interestingly enough, also in Moscow, for some reason, it's not clear why they didn't know about each other. Or maybe they knew. I asked them about goodness, and he told me that the way we're thinking about it, it's more like Pinsker, which is probably true. But still, the basic definition of expander in a slightly different language, but completely equivalent, was defined by Kolmogorov. Anyway, expander graph, I guess that in this, there are few people who know it so much better than me, which I know, and probably almost everyone knows, but expander graph is basically a graph which is sparse, but very much connected. Like for every subset, which is not too big, of course, it will take the full set. It has no boundary, but if we take a subset, which is, say, not more than half of the edges, half of the vertices, many edges are going out. So non-expander, so this is a non-expander. Because here I can cut it into two pieces with few depth. Now, the definition is very elementary. The construct and the basic result, which was true by Pinsker, but also by Kolmogorov and Brezhnev, was that if you take a fixed K, a K regular graph on n vertices, a random one, with a high probability is going to be an expanded graph. It was discovered later in graph theory. Before that, it was known even in manifold theory. Actually, it was done in Tel Aviv. The main name associated with that is Noga Alon and Vitaly Milman. That this is the spectral property that being expanded can be expressed using the spectrum of the graph, the eigenvalue of the just symmetric of the graph. And this notion extremely important in computer science, and I'm sure all of you or most of you know about some kind of applications of it to computer science. But I want to, as I said, I want to in this talk to talk about the connection with pure mathematics. Pure mathematics and even very deep mathematics was extremely useful in this context because after the results that after the notion was invented and turned out to be extremely useful, and then the only way, which was known at the beginning, was only by random method. And people wanted explicit construction. And then came the first big breakthrough by Grisha Margulis, one of the greatest mathematicians of the 20th century. He got all the prizes. One of the few got Fields, Wolf, and Abel. And luckily, it was not considered good enough in Moscow for reasons you can guess to get a position at the University of Moscow. But the head of Institute of Information Transmission there, nowadays probably it would be called Institute of Theoretical Computer Science, understood that he is one of the greatest, and he gave him a position at his institute. I heard stories from Margulis about that position there means very little salary and no work. But it was extremely important because otherwise, in those days, in the USSR, if you don't have a position, they can send you to work in the field. So he used to come there from time to time to get. There was even not a paycheck; he got it by cash. And then he felt obligated to do something related to the institute, and he heard Pinsker worked there, and he heard about the construction of about the notion of expander, and he realized very quickly that the machinery which was developed at those years by David Kashdan, then one of the brightest guys there, now professor at the Hebrew University, was exactly the machinery, something which is called Kashdan property T. It's a beautiful, it's not so difficult to understand it, but I want to continue with the history. But this was the first time that something which very pure, very deep mathematics got into the field and changed the field. Because once people understood the connection between Kashdan property T and expanders, it opened eyes in various directions. Which actually the moral lesson is that maybe anti-Semitism is not such a bad idea. Without this, we probably would not. Probably somebody would discover it at some day, but probably without it, Margulis would not hear about that problem. Anyway, the next step was this Margulis type of work, initiate more. Another work which was done here at Tel Aviv by Tzvi Galil, people still remember him here, and Ofer Gaber, the name is known.
Yes.
Did some work to compute the constant. There is equality. They got fairly good expanders, but not really as good as one work. And then the next step, which came only at the middle 80s, was by Peter Sarnak, Ralph Phillips, and me. And actually, Margulis also knew that we went a little bit more. I don't want to explain everything, to use something even deeper than Kashdan property T, but related. This is called the so-called Ramanujan conjecture, which was proved a few years earlier by Delin. If you notice, every name I'm going to mention got a Fields medal. Delin, Margulis, So for the young people who want to contribute to the area, that's there is not the Ramanujan conjecture, and we realize that the Ramanujan conjecture can be used to construct this what is now called Ramanujan graphs. And I don't have time to explain exactly, but again, coming with a big hammer to make very down-to-earth explicit construction. But what I want to tell you a little bit more, which is less known, but even from my point of view, even more exciting, that it took another decade or something like that no, even 2 decades, like in the early 20s, ideas from computer science started to influence pure mathematics. I can give a good number of examples, but maybe the most beautiful one I can draw on the blackboard, and as we say, one picture worth 1,000 words, right? So there's an area which called Apollonian circles, and in particular integral Apollonian circles. So what is Apollonian circles? Assume you have, say, okay, I'm very bad in drawing. So, I prefer to myself, second, that I will be able to copy here. I know that that's a good reason to have slides.
Maybe you can do 1,000 words.
Maybe we can help some of you.
Assume you have this is supposed to be a circle. This is supposed to be another circle. This is supposed to be a circle which is tangent to both of them, and this is supposed to be a circle which is tangent to both of them. Assume you start with four such circles. Now, every 3 of them are tangent to each other. Then you can put here a little circle. You can put here a little circle. You can put also a little circle which will tangent both, and you continue this forever. And now there is the radius of this is 1 over the radius of this is called the curvature, for a reason that I will not explain. And people were interested in integral Apollonian. What is the integral? That the radius here, we used to write, we write in 2, but it really means that the radius is 1/2. This is 2, this is 2. That is just an example, but it's kind of typical 3. So this means that this is 1 over 3, this is 1 over 2, this is 1 over 3. Now, it's known that's going back, I think, even for maybe for the Greeks or something like that if you start like that, and those are integers, these numbers that will appear here, and when I say integers, I mean 1 over an integer, will be also 1 over an integer. So people ask the following question. Still an open problem. You start like that. Are you going to get infinitely many primes in this sequence? Okay. Nice, natural question, natural at least for us, mathematician.
Come to me tomorrow.
What?
Come to me tomorrow.
Sorry? Here is a theorem which was proved by Sarnak and his people, that there exists, this is still open if there exist infinitely many numbers in this set which are almost primes in the following sense. There exists a constant C such that infinitely many numbers which will appear if you write them as a product of primes, there are at most C primes in the decomposition. These are called almost prime. Now, it may ring you a bell.
You count with multiplicity?
What?
You count with multiplicity?
Yes, you count with multiplicity. Right. Now, it may ring you a bell to one of the most famous problems in mathematics, the twin. I always, if somebody asks me for a simple problem, open problem mathematics, I talk about the twin prime because I have twins. But I think it's very, you can explain it to a child in fifth grade or something, if he knows what are prime numbers. You know, already the Greek knew that there are infinitely many primes. Of course, every prime number except of 2 is odd, which means that the distance between any 2 prime must be
At least 2.
2, at least 2. 2 primes are called twins if the distance between them is 2. So 3 and 5, 5 and 7, 11 and 13, 29 and 31. If you start to count them, we know about primes, there are infinitely many, we know to count them, etc., like up to n, how many are there, etc., etc. Are there infinitely many twin primes? This is still an open problem, which is not known. So okay, what is known there? It's known that there are infinitely many almost twin primes. Even stronger, it's known that there are infinitely many pairs. One of them is prime, and the other is a product of at most 2 primes. It's even stronger than what was put. What is common to both methods is what's called the sieve method, the classical sieve method. Now, the surprising thing which came here, the sieve method classically was applied on a billion issues, like on the integers. Here, I don't have the time to explain, but it's applying on a nanobillion situation. There is a group acting here, which is very nanobillion, and you apply similarly sieve method in a completely unexpected way. What is the crucial issue? What is the crucial point of the proof? That if you take the group SL2P with the standard generators, these are expanders. So the area of expanders contributed to this group. So this was kind of something very beautiful. And there are others. I myself was involved in proving a theorem about 3 manifold, hyperbolic 3 manifold. If you happen to hear, it's a big subject in geometry, and there was a problem about the covers. And we solved it using expanders. So suddenly the expanders came out into pure mathematics. Oh my God. It's 50 minutes talk or an hour? By 12 I have to finish. Okay, so I have to rush up. Okay. You know what, okay, now what mathematicians are very good at? Generalization. That's what we know to do. And the next step for mathematician in this area was to go from expander to I-dimensional expanders. Again, I thought to give a slightly more
In depth?
what?
In depth? The word in depth? No, never mind.
No, it's a I-dimensional expander, and
You wanted to give us more in-depth explanation.
right. Such issue, but this is even more complicated. I will skip the definition. Again, I will illustrate it by a picture. I-dimensional expander. I-dimensional expander is a generalization of the definition of expander to higher dimensional. I will illustrate in a very special case due to Gromov and a theorem of Gromov, which doesn't say expanders at all. But if you think about it a little bit, you see expanders and I-dimensional expanders. And the theorem says the following. The story is even more elaborate. In the 80s, two young Hungarian guys, by now they are quite well-known mathematicians, computer scientists, forgot the names, solved as an undergraduate the problem of Erdos. The problem was the following very simple type of question. Erdos conjectured that if you put n points on the plane and then you start to draw all the possible triangles between them. So all possible triangles between every 3 of them. So if we have n point, we have n choose 3 triangles, right? What they prove that there exists a point Z in the plane which is covered by 2/27 and choose 3, plus little o of 1 if you want to, plus minus it, if you want to be precise, of the triangle. Okay.
This is tight.
I got instruction, nothing to get out from this.
This is tight.
What?
Is this tight?
This is a good question. This is tight, the 2/27. This was proved after that.
I think it's 2/9 if you write.
What?
Like, I think it's 2/9 if you write n choose 3. Otherwise, it's
No, I think it's 2/27 unless.
2/27
But
times.
you know, I'm the guy start dimension, so every dimension.
You meant maybe
You mean-
Imre
I
Bat?
think it's 2/27. I tell you why. Why I think it's 2/27. 2/27 appears in mathematics in other areas mysteriously. I remember that I tried to see if there is a connection. The number of groups of order at most n, finite groups, is n to the 2/27 log n square. And I wonder if there is connection. Probably not. It's probably just question.
What about the
What was the
nine-dimensional dimension?
What?
What about high-dimensional dimension?
Dimension.
What was the conjecture of Erdős? This one?
What?
The conjecture of Erdős. It started.
Yeah. Yeah, I'm not sure if he gave the number, but yeah, he conjectures that there exists a constant such that that's the positive. No, both and Freud. I guess some of you may know them because they are quite well known in combinatorics and but they proved it when they were undergraduates. But that's in Hungary, not Hungary, Knesset. Anyway, very quickly after that, Barani proved an higher dimensional version of it. You can imagine what does it mean higher dimensional. Anyway, Gromov proved an amazing theory. Amazing. What Gromov said, he got into this, but nowadays this is one of the standard results in the area called convexity. Gromov proved the following. He proved that if you now do something else, now don't connect the 3 points by straight line. Make all the triangles, but in any way you want. So, and then what? The theorem is still correct. With the same number, 27. Tell you the truth, Gromov is the greatest. But his style of writing is not the greatest. I read it for the first time. I thought it must be a mistake because you see, let's say that you put on them and then you discover that there is this C, which is in many of them. I can avoid it completely. I can make the triangles. You see, I make the triangles very narrow. I connect this one and this one by this line, very, very narrow. I will connect even this line and this line, but instead of this, I will go here. And I will do it. I will take all the lines between the vertices to go to some corner. I will run away from it. But this is like the story of the Alibaba in Baghdad. You remember this story that Malach Amar, I don't know, say it in English, was supposed to meet somebody, and then he escaped to Baghdad, and then Malach Amar got him there, and then he said, "How did you get me?" He said, "In my order, it was telling that you will be in Baghdad and not in your town." Anyway, and then here's the point you will find it, a point which is covered by 9/27 and choose 3 of this French triangle. Moreover, Gromov proved the higher dimensional version of this theorem with constant, which was better that was known before for the affine, for the straight line. Okay, I don't have time to talk about it, but it was kind of an amazing work. What was even more amazing, that this is related to expander. In high-dimensional expander, something called co-boundary expander with cohomology. I don't have time to explain. He asked a question, you see, let me give you an exercise. Think about this version for one-dimensional, and you'll see why this is related to expander. This is kind of a two-dimensional version. Anyway, in the classical theory of expanders, to prove that the complete
But
graph.
in the expander version, at least the one I mentioned, every point, almost every point is deep, not just that there exists a point, right? That's the standard, right? Every point, you have a height, like a ladder.
And
You're just going,
if you do it on a line,
yes. Is it true?
so you might, at every point in
Every
some
point in
interval. Yeah, that's probably true. But there's a question what you mean by that exactly, but I think you may have. I didn't think about that. Anyway, he put forward the question, you see, with graph, with expanders, to say that the complete graph is an expander is a triviality, right? The whole point is to get sparse graphs of bounded degree. He put this question forward. You can ask it in both versions, geometric expander, which was more like the both already. You can ask it anyway. Part of it, he answered himself with Fox, probably known here, and Asaf Naor, and Pach, and one more name. See a space, but I forgot. And but the essential problem was to do it so with a bounded degree simplicial complex. I-dimensional expander. This was solved by Kashdan, Tali Kaufman, and me for dimension 2, and then my student Shai Brian, Tali in higher dimensional. Anyway, this was a lot of excitement, but usually people talk about that, and the less talk about the technical part of it, which is using some cohomology over F2, which is not a difficult subject. Actually, I gave several times that this was something like 15 years ago, 10 years ago. I felt like a missionary, and I claimed that computer science people should know about cohomology. Cohomology over F2 is very simple. It's linear algebra, elementary linear algebra. I gave sometimes talks about cohomological method for computer science. One day, if you want, to come again. It's a bit more technical, but it's completely elementary. Anyway, then I wrote a little paper with Tali Kaufman, which probably is the most trivial paper I ever written and one of the most influential, because we pointed out, and only now I'm starting my real talk, that this notion of I-dimensional expander with a cohomology is a testability result related to testability in computer science. This I'm going to define. From now on, I try to be more precise. And anyway, this testability, what is testability? Actually, that's something very, very easy to explain. I mean, I'm sure there are many people, I know some, you know it much better than I know it, but I guess many of you know, you have a problem, you want to test, you have some huge data, you want to pick up only very, very little information, you want to check very, very few bits. The classical thing is, let's talk about one of the easiest, maybe because of the lack of time, and let me take right away one of the simplest type of problem. I guess everyone here knows what is an error correcting code. An error correcting code for us, let's say linear error correcting code, doesn't matter. We take the field of order 2, 0, 1, we take a linear subspace of field C. It's an error correcting code, and we can talk about its dimension. Let's define it. The dimension of C, we just call it K, and the distance of C, this is the minimum of the Hamming distance between alpha and beta over all alpha given with beta and C. And it's clear why we are interested in things like that, right? We want to embed K bit of information inside N bit of information such that if there are mistakes when we send it over a noisy channel, we will be able to correct it to this. So this is, it's going back to Shannon, who say that C is a good code. Okay, I have to say, we are mathematicians, not engineers. So we care about N going to infinity, right? Not about a specific example. Good code, which is really a good code, is if K over N and D over N are both bounded away from 0. Like the distance and the rate grows linearly with n. Sometimes people call the rate k over n. This is the normalized distance. Anyway, this is good codes according to Shannon. That's a standard terminology. What is local testable code? Local testable means that given alpha in F2 to the n, I want to check whether alpha is in the code or not. Then we say that this is locally testable code. The code is locally testable. That's a typical definition to any subset of some set. If there exists an algorithm that reads only u bits out of n, and the most important thing that this q is independent of n. N can be zillion, and I read only 25 bits out of the code, and I want to decide by reading only 25 bits whether the vector is inside the code or not. This is, of course, impossible. What I really want to decide whether it is very close to the code in the Amic distance or not. Like assume I have an error correcting code which can correct 2%. Usually, I can correct 2%, 5%. If there are 40% mistakes, there is no chance to correct. If there are 50, even theoretically, there is no chance to correct a vector that I got. The receiver is getting a vector. You want to check if it's close. He has an algorithm which for error correcting code, but it doesn't have to read 200,000 bits in order to discover that it's completely corrupted. You want to read only 70 bits, and if it's too far, to check it again. So what you want, you read only Q, and the algorithm answer yes if alpha is in C, so we don't allow mistake in this direction, and no with probability at least some fixed epsilon. There exists fixed q and fixed epsilon. At least epsilon, the normalized distance, 1 over n, the distance between alpha and the code. Namely, if the code is really far, it will be discovered with high probability. If it's not, and you don't have to worry about it, what is the exact probability, because you can repeat the test 7 times, it's still bounded number of bits, and you can make this probability as small as you want. Well, as small as not. Anyway, okay, so this was a long-standing problem from the 90s. Actually, the famous work of Spielmann and Sipser, the so-called expander code, for which it was one of the main reasons that Spielmann got the Nevalina Prize at the time, was really because he constructed LDPC code, whatever it means, good cause. But really, in his thesis, which was done under the guidance of Sipser at MIT, he wrote that he wanted to get LTC. He couldn't get LTC. He got LDPC, whatever it means, which is weaker. And this remained an open problem for some 30 years. Amazingly, even though it was one of the most famous problems in correcting codes, it was solved completely independently at the same week. 2 papers were put on the archive. And the answer is theorem. There exists good LTC codes. And this was proved independently by Irit Dinur, Shai Evra, Ron Livne, me, and Sharon Moses. And at the same time, by Panteliv and Kalcher It's not a mistake. They write always in their paper this way in Moscow. They came from completely different direction. They solved the problem in quantum correcting codes, and as a corollary, they deduced this, and we came with that. Eventually, the proof are not that different as it sounds. But the whole point is that we both use high-dimensional expanders in some way or another, which unfortunately I don't have time to say because the time is almost over with all my stories. Anyway, this was nowadays high-dimensional expander in computer science all around. You know, when you read the new cut into the subject, she made so many directions. It helped recently also with improving the PCP theorem, etc. There have been always several little conferences, and in a few months from now, there is going to be a full semester in the Weizmann Institute in Berkeley. There's for computer science about high-dimensional expander. So this is actually an interesting intellectual story. Expander came to pure mathematics. First of all, pure mathematics ended with expander. Expander pure mathematics. The mathematician kind of extended the notion. High-dimensional expander certainly came from us. We use chaotic Lie groups, current theory, buildings. I don't want to get on you. And then suddenly, the computer science picked it up, and I said that my little paper with Tali was kind of an influential in this direction. They realized that it has something to do with testability. And now it became a big subject. Now I want to start a third talk in the following sense, and I hope it's like that's exactly the experiment I'm doing with you. I kind of have some hope. I want to attract your attention to a notion of testability, which was developed within pure mathematics. So far, I don't know application in computer science, but I do hope that something similar will happen, and you guys will discover that this is that. And even on a you know, old people like to tell stories about their past. And it really, I started to work on it completely accidentally. I was in Switzerland in a conference about high-dimensional expanders. And then, you know, in every conference, usually in one of the afternoon, there is a walking tour, like, you know, you go for a walk. Switzerland is so beautiful, and the Swiss people know to enjoy their life. Every day there was a walking tour, lectures in the morning, and then a tour, and then another set of lectures in the evening. That's the style there. Anyway, I was walking and talking with a mathematician from Vienna, Gulnara Arjesteva, and she told me about the little theorem that she proved with Livio Conesco. And let me write down the theory. This is Arjesteva and Conesco. It's around 2015 or something like that. They proved the following. Given, for the epsilon, there exists delta, such that given two permutation AN and BN in the symmetric group on N, such that AN and BN almost commute. What does it mean they almost commute? The distance between AN BN and BN AN is less than delta. What is the distance between two permutations? That's very simple. The distance between two permutations, tau and sigma, is 1 over n, the number of I in n, so that tau I is not equal to sigma. So AN and BN agree on 99% of the entries between 1 to n. Then how can you get such permutation? The easiest way, take two permutations which two commute and smash them a bit, right? This is the inverse theorem. If it's less than delta, then there exists AN prime, BN prime in sim n. which truly commute. A n prime, b n prime is equal to b n prime, a n prime, and the distance between a n to a n prime and the distance between bn and bn prime is less than epsilon. Okay. Why they care about theorem like that? There is a long tradition in mathematical physics to study problems like that among matrices. Related to the Heisenberg uncertainty problem, etc. You take two matrices, and which almost commute. Are they nearby matrices which truly commute? There are dozens of papers about that, asking it in a different context. Assume you have two matrices which are self-adjoint, which almost commute. Are they nearby self-adjoint operator which almost commute? Now, also nearby, what does it mean? In what metric? There are many different natural norms on the n by n matrices, complex matrices. Now we n go to infinity. The most important thing that I hope it was clear that epsilon delta are independent of n. By the way, there are two papers with the following titles, more or less. One says nearly commuting matrices are near commuting matrices. One says not every nearly commuting matrices are near commuting matrices. And don't worry, both papers are correct. And there is no fundamental contradiction.
Nearly correct.
Both are correct. The question is, what is the metric? In the Hilbert-Schmidt norm, for example, whatever it means, that this is the case. In the operator norm, it's not. It's a famous counterexample of Pascalesco. I mean, so there are a lot of problems, and they decided to study this in the discrete level. They didn't really have a real strong motivation. They were curious about it. Now, well, actually, there's some motivation. Look at this theorem. Do you see that this is testability results? Right? I don't have time to explain, but it's exercise. The theorem really says the following. It says, I give you two matrices, a two permutation, and I ask you, do they commute? Now, you want to check, now the code now, the non-abelian code, is all the AB, so that AB, this is the code, all the pairs of permutation which commute with each other. And the question is, are you near the code, right? So you pick up some few i's between random few i between I to n, and if they all satisfy ABI equal BAI for this random number, because of the theorem, you are nearby the code. So these are the testability results. At that time, I was very much working on this testable code and all this. So I said, wow, my two loves of group theory and testability can be emerged, and I started to work on it very intensively. I want to tell you only a few stories and present you some open problems. Now, okay, so in group theory, basically what we say with the now I'm working with the permutation groups and the normalized Hamming distance. You can ask all these questions also in other contexts, in the unitary groups and various other methods. But let's stick to the permutation. So we say, if W is this equation, the equation AB equal BA is stable, which really means that if you pick up a good number of i's and they satisfy the equation, you are nearby permutation satisfied. You can ask it on other equations or even system of equations. For example, what do you think about so let's call it V1, W1, V2 it will be another equation. What about this one? AB equal B squared. Okay. Is this stable? What about this one? A square B equal B A cubed, say. Are they stable? So you understand what I mean? Is it true that almost solutions are nearby solutions? Do you have a guess?
Two possibilities.
Right. Now, and you can ask why to look only at one equation. I can write a sequence of equation and say assume all of them are almost satisfied. Are there nearby? This is called stability. Here is a very important observation which appeared in their work, appeared maybe even earlier in the work of Glebsky and Riviera, a paper which appeared in the Taiwanese Journal of Mathematics. At that time, I guess not too many people paid attention to that. And they made the following observation that I have to skip the proof, but believe me, it's a very simple proof. They say the following: you have a system of equation W, one equation or a system of equation on generators A, B, or even on 17 generators. Look at the group gamma, which is defined by the generators A, B, C, and the relations W. Namely, you take the free group of the generators and you think of this, if you take everything to the other side, you get a word in the free group, and you look at the normal closure of this word, you get a group, an infinite group. The claim is that the answer, whether the system of equation is stable or not, or testable if you want, depends only on the group and not on the system. This should ring a bell to those who learned a little bit mathematics to Galois theory. What happened in Galois theory? In the classical Galois theory, you have a polynomial, you want to ask whether the polynomial is solvable, right? You associate a group to it, and the big work of Abel, Galois, and all this was that the polynomial is solvable if and only if the group is solvable. That's why we call it solvable nowadays. This condition, but to check whether the group is solvable is very easy. To check now, because it depends only on the group, it doesn't matter if the presentation comes with W or W prime or something. You see, the same group can be presented in many different ways. Either all the systems are stable or not. Okay? So now we have a good definition. A group is stable if and only if one of its presentation is stable, if and only if all the presentations are stable, and we are now in the middle of developing techniques to decide whether they are testable or not. Now, I don't have time to present any of this technique. I hope I will, but I want to warn you. We can answer various questions. For example, this is indeed stable, but this is not. But the only way I know to prove it is because of the connection to group theory. This gives a group which called Baumschlag Solitar 1, 2, and this gives Baumschlag Solitar 2, 3. But they are very different in their behavior, some of these two groups. And therefore, by analyzing some, I don't know, not very difficult, but still some deeper properties of the group, we can answer. We don't know, and like the no here is. Maybe I will finish with an open problem, which is very elementary. Okay, here the answer is no. Namely, for some sequence of n going to infinity, not necessarily for all of them, but sequence going to infinity, I can find a permutation an and bn, which almost satisfy this property, but they are bounded away. They are not nearby a permutation satisfied. I have no idea how to do it. I have no idea how to do it. The proof is using amenability, Sophie groups, etc., etc. Maybe I will not try to push on you too much. It's related to one of the most outstanding problems in group theory, whether every group is Sophic. Sophic is a notion of our friend, defined by our friend Benji Weiss, who just got the Israel Prize in mathematics 2 weeks ago. And it's a big problem whether every group is Sophic or not. And this study of stability gives some way to attack this problem so far, without success, I want to stress. Still, there was some partial success, which looked impossible like years ago, but they are solving many problems, but not the most important ones. Because as I said, we can define the notion of Sophic also, and all these notions also for unitary groups in many different matrix. In the other categories, we can solve it using this type of ideas. And that anyway, I have to say, I was deeply influenced thinking all this problem by computer science, by testability. I think about it all the time as a testability problem. I try to make some propaganda for you. Maybe you can take this type of stability back to your area, because this is a natural problem, I think, from a computer science point of view, whether a problem is testable or not. Okay.